Good morning. I'm Professor Raphaël Khoury from Université du Québec at Chicoutimi. And today I'm going to talk to you about some research that I performed with my colleagues, Sylvain, also from Université du Québec at Chicoutimi, Professor Hamoulaj from Concordia, and our students Benjamin Vigneault and Asma. And the purpose of this research is to study the use of vulnerabilities, especially CSVs, which are vulnerabilities that are documented in a database called the NVD, by IoT malware. So over the last 10 years or so, there's been an exponential rise in the use of IoT devices, and consequently, an equivalent rise in the presence of IoT malware. And in our previous research, we looked at IoT malware, and we found that it's generally developed independently from malware that targets other platforms. But IoT malware developers tend to borrow a lot from each other. So especially they borrow features. So what happens is that a new feature is introduced in a malware. So that might be a new scanning strategy or a new attack vector. And if that feature is successful, if the malware that contains that feature is effective, then other subsequent malware will include that feature. So that might be because the malware developer reused code, but we found that even in the absence of code reuse, just the knowledge that a feature exists, then it'll be re-implemented by other malware developers because the code of malware is not always available. And one feature in particular that's especially interesting is the use of vulnerabilities as an attack vector. So the earliest malwares, IoT malwares, usually infected their victims through credential attacks. So usually brute forcing credentials or credential dictionaries. But then starting a few years ago, we began to see IoT malware that exploited vulnerabilities on the target device. And so that was one feature that we looked into when we were looking at the feature-based analysis of the evolution of IoT malware. And in this paper, we dig deeper in that specific feature. So we will distinguish between two types of vulnerabilities. One type is CVEs. These are vulnerabilities that are documented and logged in the database called the National Vulnerability Directory. National Vulnerability Database, sorry. These are CVEs, and the other type are vulnerabilities that are not in that database, so they're non-CVE vulnerabilities. So that's the language we will use in this study. And so we focus on three research questions. The first are what trends are detectable on the use of vulnerabilities by IoT malware, is it growing, and so on. Second, we look specifically at CVEs that are used by IoT malware developers, and we want to see if they differ from CVEs that are not exploited, the ones that are passed over by IoT developers. And in fact, we will find that these are the ones that are selected really are different from the ones that are passed over. And so the third question is, since CVEs that are exploited by IoT malware developers differ from the ones that are not exploited, well, can we use that knowledge to predict if a vulnerability will be exploited or not? So this will help code developers to prioritize the vulnerabilities in their projects. So in addition to these three, answering these three research questions, another contribution of this paper is that we provide a lot of background information about the use of vulnerabilities by IoT malware. I'll introduce these as I go through the paper. Amongst other things, we include a list of every CVE that is exploited by an IoT malware, with which malware exploits it, and the reference to where we found out that this malware exploits that vulnerability. And we believe that this type of information will be very useful in the future for security researchers. So here's the data that we looked at. So first, the malware, we looked at 27 IoT malware spanning a period of a bit more than 10 years, from 2008 to 2019. So these 27 IoT malware, that's actually every IoT malware that's well documented in the academic literature. There's two other that are too recent to be mentioned a lot in the academic literature, but that are mentioned in reputable websites on malware. So that's basically the entire corpus of malware, IoT malware. And we looked at the National Vulnerability Database. So this is a very well-known database by computer security researchers. It's maintained by a US government agency called NIST. And it contains 140,000 entries. So each entry is a vulnerability. There's a unique identifier with a number and some background information about the vulnerability. So there's a list of systems that are affected because for each vulnerability, the vulnerability might affect multiple systems. So there's a list of affected systems, and there's a rating that describes how easy it is to exploit it, attack vector, impact score, and there's a vulnerability type called CWE that I will get back to in an instant. So the NVD spans 20 years. It's a fairly long period of time. We chose to include the entire database in our study because some malware reaches back several years to select vulnerabilities to exploit. In fact, the earliest vulnerability that is being exploited by IoT malware is a vulnerability from 2003 that is exploited by EcoBot, which was published in 2019. So if we went back many years to find this vulnerability and choose this one for exploitation. The NVD dates back basically from 2002. So the first question is, which trends are visible in the use of vulnerabilities by IoT malware? So in this slide, you can see a summary of the data that we gathered. More detailed data is present in the paper. So here is just a graph, but in the paper, there's a table with all the information broken down by malware. So this is the cumulative number of vulnerabilities that are exploited by IoT malware by year. In blue, there are CVE vulnerabilities, the one that are documented in the NVD database, and in orange, there are non-CVE vulnerabilities. So there's two conclusions we can draw just looking at that graph. So first, in recent years, there's been a sharp increase in the use of vulnerabilities by IoT malware. The earlier IoT malware, they really preferred credential attacks or brute forcing credentials or credential dictionaries. There were a few that used mostly non-CVE vulnerabilities. But then starting in 2016, just the use of vulnerabilities really became the almost default attack vector against IoTs. And the second thing we can see is that this NVD database really seems to be the preferred source for finding vulnerabilities by IoT malware developers. The CVE vulnerabilities outnumber non-CVE vulnerabilities by a factor of 4. So there is a small threat to vulnerability that I want to be open about in this respect. Is that in some cases, there was an entry in the NVD for vulnerability, but we believe it's possible that the entry was only created after the vulnerability was exploited by malware. So in that case, the vulnerability is mischaracterized in this graph, but we believe it's not so frequent as to alter the result of this data. Another thing that skews these results a little bit is the fact that a single malware, EcoBot, uses a lot of vulnerabilities, 73 CVEs and 19 non-CVE vulnerabilities. So this single malware skews the results a lot. EcoBot is a very recent malware published in 2019, and it's very dynamic. It was updated several times with the addition of new vulnerabilities. So it remains to be seen if other future malware will follow the lead of EcoBot in aggressively using CVEs. One thing we see is earlier malware, when they use vulnerabilities, they only use one vulnerability. Another thing we looked at in our previous research is the objectives that IoT malware might have. So we found 5 different objectives. Malware might serve the purpose of creating denial of service attacks. Actually, that's the earliest objective and the most common one. We found at least one IoT malware whose purpose seemed to have been the physical destruction of the target device. There's income generation, an increasingly common objective, so that might be crypto mining or ransomware. Spying, leaking data, or the dissemination of other malware. So these are the 5 objectives that we found. Some IoT malware might have multiple objectives at the same time. So we wondered if there's a correlation between these objectives and the use of vulnerabilities. Is it possible that malware with a specific objective is more likely to use vulnerabilities as an attack vector? Malware with a different objective is less likely and prefers credentials attacks. So we were unable to find a correlation, unfortunately. This is in part because some of these objectives only occur in 1 or 2 malware, and some of these objectives only occur toward the end of the period that we were looking into. So that made it harder to find the statistically meaningful correlation. So as I mentioned, this paper includes a list of every IoT malware, what are its objective or objectives, and how many CVEs and non-CVE vulnerabilities it exploits, and the listing of every CVE with the number and a reference. So the second research question that we looked into is the CVE, the ones that are repertoried in the NVD database, how do they differ from the ones that are not selected for exploitation? Some background first. So out of the 27 malware that we looked into, 11 made use of vulnerabilities as an attack vector. And in total, these 11 used 99 CVEs, a total of 128 times. So that's counting each use of a CVE by a different malware separate. So naturally, you can see that some vulnerabilities, some CVEs are used by more than one malware. And of these 99, so in the database, there's 2 ratings that describe different pieces of information that I'll introduce in a moment. So there's CVSS version 2 rating and the CVSS version 3 rating. So in the rest of this presentation, I'm going to call them V2 and V3. And not every vulnerability has both ratings. So every vulnerability that we looked into had the V2 rating, except one. So 98 of the 99 CVs had the V2 rating, and 64 had the V3 rating. And so only one vulnerability had neither, and we believe that it's a duplicate of another vulnerability in the dataset, in the 99. So these things are not always certain. Okay, so what did we find about the vulnerabilities that are exploited by IoT malware developers? So the first thing is each entry in the CVE explains the attack vector for the attack, for exploiting the vulnerability. So this can be one of 4 values: network, when you can exploit the vulnerability across the network; local, when you need to be in the local area network; physical, if you need physical access to the device or adjacent network. So it's a bit unsurprising, but every vulnerability that was exploited by IoT malware developer uses the network access vector. It's not very surprising, but we thought it worthwhile to mention it anyway. Malware developers also prefer vulnerabilities that don't necessitate user interaction. So that's another information that's mentioned in both V2 and V3 rating scores. So 93% of the vulnerabilities that are exploited and for which there's a V2 ranking do not necessitate user interaction versus 68% for the NVD in general. And for those that have a V3 score, It's 92% that don't necessitate user interaction versus 36.9% NVD in general. So we use the Z-test to confirm the statistical validity of these results. Anytime that I will give you these types of numbers in research question 2, there's always a statistical test that was performed to confirm the validity of the results. So the V2 scoring also provides a three-valued verdict regarding the difficulty of exploiting the vulnerability. It's either high, medium, or low. And for the V3 score, it's a two-valued verdict, high or low. And once again, we can find that IoT malware developers prefer vulnerabilities with lower exploit difficulty. So again, we performed the key score tests and we could find with strong confidence that they prefer easier to exploit CVEs, and this result holds for both V2 and V3 rank. In addition to selecting attacks with lower complexities, IoT malware developers seem to prefer vulnerabilities with higher impact score. So both the V2 and the V3 rating systems provide an impact score for each vulnerability, and it goes from 0 to 10. And the average for the vulnerabilities that are exploited by IoT malware developers is 8.1 and 5.6 respectively for V2 and V3 scores. And this is higher by a statistically significant margin than the average for the NVD in general, which is 6 or 4.4. So another interesting thing is each CVE includes a single CWE. So that's the type of vulnerability. And it's taken from a different database maintained also by NASD. So CWE is a common weakness identification. So weakness is basically a type of vulnerability. So in this table, you can see the top 6 CWEs that are exploited by IoT malware developers, and the proportion in the central column of IoT malware that of CVEs used in IoT malware that is of each type, and in the right-hand column, the proportion in the NVD in general. So you can see that except for the 5th buffer overflow, the other 6 are overrepresented in the corpus of exploited CVEs. One thing that's interesting about this is that several of them are related to injection attacks. So the first 2 are 2 different types of injection attacks. The third is input validation, which is also in some respect related to injection, and the fourth also another type of injection. Then there's buffer overflow, which, as I mentioned, is actually underrepresented in the exploited vulnerabilities. And the last is authentication error. This is also interesting because aside from exploiting vulnerabilities, the other preferred attack vector for IoT malware is credential attacks. And again, we use the key square test to ascertain the statistical validity of these results. There is another threat to validity that I want to discuss at this point, is that unlike all the other aspects that all the other elements of the CVE entry that I mentioned before, the CWE, this varies a lot from year to year. Some years, buffer overflow might be very frequent, and other years, it might be rarer, comparatively rarer. The other elements of the CVE rating, they're more constant over the years. They're like the attack difficulty and the attack access vector and so on. So because our database skews towards more recent vulnerabilities, this is something we did not control for in these numbers. So as I mentioned, some malware developer exploit vulnerabilities that are several years old. So I mentioned that one vulnerability was from 2003 and used by EcoBot in 2019. But that's unusual. In practice, most vulnerabilities are less than 2 years old, and especially less than 6 months old when they're exploited by IoT malware. So in this table, you can see intervals of number of months and how many vulnerabilities in our corpus in the 1998 were that old in months when they were incorporated in the malware. And on the right, you can see it's the same number as in the center, but broken down for each malware. So E is EcoBot, E is Darols, and so on. All the malware that we looked into in our experiments. So unfortunately, we were only able to obtain partial data about this information. What happens is that for several IoT malware, they make use of vulnerabilities, but we're unable to ascertain exactly when the vulnerability was incorporated into the malware. The reason is that the malware can be updated several times and updated with the inclusion of new vulnerabilities, and we won't know exactly when the incorporation happens. So one thing that is good is that we were able to obtain the information for EcoBot. So EcoBot was updated several times with the inclusion of multiple vulnerabilities, but we were able to pinpoint several dates when that month there was an update with these are the vulnerabilities that were included in EcoBot that month. So all this information is more detailed in the paper. So the main conclusions that we get looking at this table is malware really tends to prefer recent vulnerabilities, but there's one exception, and that exception is EcoBot. EcoBot seems to have two different strategies, either very recent malware, less than 6 months, or very dated entries, less than more than 2 years. And it seemed that another security researcher wrote that EcoBots seem to be targeting either systems that have not yet been patched or systems that were no longer maintained. So it remains to be seen if other malware, future malware, will use the same strategy as EcoBot. And it's very likely that this will be the case because EcoBot has been very successful. And what we found in our research is that when a malware is successful, other IoT malware adopts the same features that it had. So we can see this dual strategy of very old vulnerabilities and very recent vulnerabilities as a feature, and that it will be adopted by future malware. So the other thing that we noted is that some CVEs are exploited by multiple IoT bots. So of the 99 CVEs in our corpus, 13 are exploited at least twice, 8 are exploited at least 3 times, and 2 are exploited 4 times. So what we conclude is that if a vulnerability has been exploited in the past, it's more than 8 times more likely to be exploited again in a different IoT malware. This might be because of code reuse, but as I mentioned earlier, the code is not always available. But even when it's not available, IoT malware developers just borrow the idea of doing something feature. So the exploit code might be recoded over and over again. So having found that vulnerabilities that are exploited by IoT malware developers differ from the ones that are not exploited, our final question is to ask if that information can help us predict if a given vulnerability is likely or unlikely to be exploited by IoT malware developers. So this could help code developers prioritize the vulnerabilities that are found in your code. This could also have other applications in developing defensive mechanisms. So we used a machine learning process. So in this research question, we did not want to use the entire NVD database. So we performed a first filter to identify products that were specifically targeted to identify CVEs that targeted IoT devices. I explained in the paper how this filter was made. At the end of this process, we had 6,300 CVE entries that targeted IoT devices. Some of them did not target exclusively IoT devices. The reason is The reason is some CVEs can exploit can target multiple platforms, but all the 6,300 exploited at least some IoT devices and possibly also other devices. So for each of these 6,300, we created a feature vector that had the following information. So the year of publication, the CWE, so the type of vulnerability, and a lot of different information that are present in the V2 and V3 rating. So access complexity, user interaction that I mentioned already. There's an exploitability score, impact score. And when we had both the V2 and the V3 rating, we included both. The vector, we had only V3, only V2. We included only the ones that we had. We had V2 for every vulnerability. So each vector also included a Boolean value that indicated if the CVE is related exclusively to IoT products, or if it also additionally targets other types of devices. And then there were the two classes selected, the vulnerabilities that have been exploited by IoT malware developers and those that were unused, that were not selected for exploitation. So the dataset was heavily unbalanced, 98 CVEs selected and 6,300 in total. So we used undersampling to correct the imbalance. I do recognize that this is another threat to the validity of the results. Future research might alleviate this problem. So here are our main conclusions. So we used 3 different clustering algorithms, and what you can see is that we were able to predict with high precision and high recall if a vulnerability is likely or unlikely to be exploited by IoT malware. So in conclusion, we found that IoT malware increasingly relies upon the exploitation of vulnerabilities as an infection vector, and that the NVD seems to be the preferred source to obtain these vulnerabilities. We also found that the vulnerabilities that are selected by IoT malware developers differ from the broader NVD in several respects. As I mentioned earlier, they use network as the attack vector, easier to exploit, higher impact factor, less likely to necessitate user interaction, and so on. And we found that these differences are sufficiently salient to permit automated prediction using machine learning algorithms. So there are some threats to validity in our study. I mentioned some of them earlier. I believe in science, it's important to be open about any threat to validity. So as I mentioned, there's a threat to validity to the fact that we use the entire NVD database as a reference. And this was a conscious choice because some IoT malware do reach back several years to select vulnerabilities to exploit. But many others do not. And most exploit vulnerabilities that are about at most 2 years old. So that's a threat to validity. And it's a threat to the result that I gave with respect to the CWEs, because the number of vulnerabilities with each CWE type varies a lot from year to year. So the incompleteness of the data is another factor that weakens the validity of the results. So the V2 and V3 rating were not included for every vulnerability in the database. Also, it's well known that some entries in the NVD are duplicates. There's one in the 99 that we believe is a duplicate of another, the 99 exploited vulnerabilities. Another potential weakness of the validity of our results comes from the fact that some vulnerabilities receive the CVE entry only after they began to be exploited by IoT malware, and we were unable to control for that. So this is a weakness in the first part of research question 1. Thank you.